For the left people first, left-brained, a root of x times b root of y equals ab times root xy. For the right-brain wordy people, multiply the coefficients. Multiply the coefficients. Multiply the radicands. Simplify if necessary. To the left brain wordy people, coefficient times coefficient, radicand times radicand, simplify. And just back up to the top, a rule that's going to come up in grade 12, it's going to come up in IB, it's going to come up in calculus, this comes up over and over and over. What is root of x times itself? So for example, root 3 times root 3. Well, if we follow this guide, we would multiply the radicand. So root 3 times root 3 would be root 9. And what is the root of 9? So root of x times root of x always equals x. So any root times itself just equals the radicand. That's right, I'm double highlighting it. That's how important it is. Comes up over and over and over and over again. Okay, so let's practice. These are going to look scary at first because there's roots all over the place and there's brackets and there's numbers. It's no different than grade 9 algebra. So in grade 9, we introduced you to the same thing. It just happened to have x's and exponents and y's and coefficients. We use distribution just like we did before. So we're going to multiply 2 root 5 by root 3. And then we're going to multiply 2 root 5 times negative 4 root 10. Coefficient times coefficient, radical times radical, simplify if you need to. So in front of the 3, I'm just going to write the imaginary 1, just so for the first example we see what's happening. So when I go to multiply these, I'm going to do coefficient times coefficient. So 2 times 1 is 2. Then radicand times radicand. Root 5 times root 3 is root 15. Okay, so coefficient times coefficient, radicand times radicand.
What was the thing with the x's? I'm sorry, I got behind.
The x, we're not using it in this example. I'll let you know when that comes up.
I still want to know. Oh, just the radicand?
We're good?
Yeah.
Okay. Now I'm going to do the same thing with the second term in the brackets. So negative 2 times, or sorry, positive 2 times negative 4 is negative 8. Radical 5 times radical 10 becomes radical 50. So again, coefficient times coefficient, radical times radical. The last step is just to simplify. Can we simplify a root of 15? So is there any factor of 15 that is a perfect square? Nope. What about 50? So either prime factor or if you can see the factor, is there a perfect square hiding within 50? What is it? 25. Okay, so I'm going to leave the 2 root 15. He's as simplified as he can be. I'm going to leave that negative 8 out front. And I'm just going to break up the 50 into 25 times 2. So that's what we did Friday. It's what we did yesterday. It's the same simplifying at the end. Keeping the 2 root 15, keeping that minus 8, not worrying about him yet. I'm going to actually take root of 25, which is, and then I'm going to leave the root 2 that we can't touch. And the very last step, which is the same as yesterday, I'm just going to combine this coefficient in front. So I'm going to leave the 2 root 15, and I'm going to multiply an 8 times 5, 40, and then follow it up with the root 2. There's the final answer of our first multiplication.
This is going really crazy.
I feel like I went a little bit fast.
A little bit.
Okay.
A little bit for this one. Yeah.
Sorry? Really? Even though the same simplifying? Because you can see the distribution? Yeah. Maybe because we already did the addition, so like you're used to the simplifying part? Example number 2, binomial times binomial. See, non-mathematicians look at a question like this, like, but everything's the same. There's 3, there's 2. As mathematicians, we're like, this is pretty. This is fun. How did you multiply 2 binomials in grade 9? So double distribution is one method. Other methods? FOIL is another method. Did anyone show you tic-tac-toe?
What?
Okay. So I'll do FOIL. Yeah, it was the tic-tac-toe. I'll do FOIL first. If you like that, great. Then ignore me when I redo it. If you don't like FOIL, then I'll show you another way. You don't have to know both. It's just 2 different ways to do the question. So FOIL is the same as double distribution. It's where we have to multiply the first times the first, the last times the last, the 2 inside terms, and the 2 outside terms. Again, it's always going to be coefficient times coefficient, radical times radical. So the first terms. The coefficient is 2 is going to be multiplied by the imaginary 1 that we don't see. So 2 times 1 is 2. Here's where we're going to use that rule we double highlighted. Root of 3 times root of 3 is just 3. And I'm just going to leave 2 times 3 for now. If your brain needs to put root of 9 first, then do that. And what is the square root of 9? 3. That's where it's coming from. Okay, so that's just our rule. Root of x times root of x is just x. Same thing here. Okay, let's do the outside terms next. So 2 times negative 1. Audience participation. Negative 2. Root of 3 times root of 2. Multiply the radicands. Root of 6. The inside terms, 3 times 1 is 3. Root of 2 times root of 3, root of 6. And the last 2 terms, 3 times minus 1 is minus 3. Root of 2 times itself, this is our little rule, root of x times root of x is 2. So again, if your brain wants to put root of 4 and then make it 2, that's fine. But that's where it's coming from. Root of 2 times root of 2 is just 2. Simplifying, I'm going to multiply the 2 times 3, and I'm going to multiply the 3 times 2 in the front and the back. So 2 times 3 is 6. At the end, I have minus 6. Here we have an addition of like terms. Just like when we FOIL with algebra, there's typically the 2 middle terms we can smush together. So if I have minus 2 root 6 and then plus 3 root 6, how many root 6s do I have? Plus 1, which I'm going to write as imaginary, root of 6.
Wait, what's the root 4 again?
So root of 2 times root of 2 is a root of 4.
Oh, yeah.
And so it turns into 2.
Oh, right.
Last thing, I'm just going to combine the numbers. What's 6 minus 6? All of this turns into root of 6. Math is so pretty. Look at all that stuff in the question, and it's all equal to root of 6.
Where did the dotted line come from?
It's imaginary 1.
Oh, right.
That's so pretty. I'm going to show you a different way to multiply two binomials. Again, if you like foiling, you can just ignore me for the next 2 minutes or so. It's just a different way. So some people do multiplying binomials with a tic-tac-toe table. The top left-hand corner is just a multiplication sign. The first binomial I'm going to put along the top, and I'm going to put one term in each box. So I'm going to put the 2 root 3 in the first box, and then the 3 root 2 in the second box. The second binomial is going to go down the side, again, one term in each box. Now I'm going to switch colors.
This is kind of like a little more complicated version, like the radical version of something that I was actually taught in grade 7.
Cool.
Yeah.
And now what we're going to do is just multiply the intersections of the boxes. So the first box is going to be root 3 times root 2. So 1 times 2 is 2. Root 3 times root 3 is 3. Can you see the light screen there?
Yeah.
Second one's going to be the intersection of a root 3 and a 3 root 2. So 1 times 3 is 3. Root 3 times root 2 is root 6. The intersection here is going to be negative 2 root 6. And the last intersection is going to be negative 3 times 2, because root 2 times root 2 is itself. And if you notice, our 4 terms that we had here when we foiled and our 4 terms within here are exactly the same. It's just a different way to do the same math. Right brains tend to like the chart. Left brains tend to like this one, whatever. And so now I'm just going to simplify. I have 6 plus 3 root 6 minus 2 root 6 minus 6. The 6's are going to cancel. And a 3 root 6 minus a 2 root 6 is just a root 6. You can use whatever method your brain likes the best. I'm just giving you options. Thumbs, how we doing? Yeah, I'm getting this, I'm kind of getting this, I'm not getting this, I'm not liking it. Good. Binomial squared. Grab your red pens. Let's go back to grade 10. How do you do a plus b squared? And then? Okay, so a times a times b, b times a, and b times b. And then what do? Combine, so I've got an a squared. It's the two middle terms I can put together. One ab and a ba, they're the same thing. How many do we have? And at the end, I've got b squared. The most common mistake is people are going to say that this is a squared plus b squared. So what have they done there to get a squared plus b squared? They've just distributed the exponent, and we don't have an exponent law when you're adding. We've got an exponent law when you're multiplying, you can just expand, but it doesn't work that way. So this does not equal a squared plus b squared. This is such a common mistake that we call it kitten killing. So every time you make that mistake, a kitten dies. Every time. And you make that mistake, I'm going to call you a kitten killer. It does not equal a squared plus b squared. Well, what does this have to do with radicals? We're going to do the exact same thing we did with algebra. So first thing we're going to do is write the binomial out twice. You can FOIL, you can tic-tac-toe, you can do any method you want. I'm going to tic-tac-toe it. Why not? Root 3 times root 3. 3. Again, if your brain went to root of 9, that's fine. Just take the next step, and the root of 9 is 3. Root of 3 times root of 6. Root 18. Root 6 times root 3. root of 18. Root of 6 times root of 6.
So 3, 18, 18, 6?
Kind of, 3 root 18.
Or, well, 3 root 18, root 18, 6.
So if you foiled, you should be at the same spot with me here.
Barely.
And so we're going to simplify. First, I'm just going to put the numbers together. So 3 plus 6. And then I'm going to add the middle terms, just like we did when we foiled above. So if I have 1 root 18 and then another root 18, how many root of 18s do we have? 2 root 18. Very last question we ask is, can we simplify? So we look at that root of 18, and is there a perfect square hiding within the factors of 18? What is the perfect square hiding within the factors of 18? 9 times 2. So I'm going to leave the 9. I'm going to leave the 2. I'm just going to deal with that root of 9 right now. And what is the square root of 9? And I'm going to leave the root of 2. And the last step, just like all the other questions, I'm just going to put those two coefficients together. We're multiplying, so 2 times 6 is, and then follow with the root 2. That's what I meant to say, yes. 2 times 3 is 6, and then follow with the root 2. I'm going to show you the same mistake someone's going to make that they would have done over here. So a really common mistake is people just distribute the 2. And they're going to say, well, the root of 3 times itself is 3, and the root of 6 times itself is 6, and they're going to say all of this equals 9. Okay, no, it doesn't work that way. You have to FOIL it, otherwise you have killed a kid. The second poster, by the way, we'll use in grade 12, and there's a whole bunch of grade 12s first semester that killed puppies. Let's not talk about it. How are we feeling so far? Example number 4. Oh, I can't talk about it right now. It's too devastating. Okay, so lots of X's going on in this one, and lots of Y's, and lots of stuff. Only difference between example 2 and 4 is now we put some variables instead of just having numbers. It's not going to change the process. It's not going to change how we do it. It just happens there's letters instead of numbers. You can FOIL, you can tic-tac-toe, you can do whatever you want. I'm going to FOIL this one because I tic-tac-toed the last one. So 2 root x times root of x, coefficient times coefficient, radical times radical. So 2 times 1, 2. Root of x times itself, x. And again, if your brain went to root of x squared, that's fine. The root of x squared is x. That's where it's coming from. The outside, negative 1 times 2 is negative 2. Root of xy, it's just root of xy. So I'm just going to put those radicands together. The insides, I've got 3 times 1 for the coefficients, which gives me 3. Root of y times root of x is just a root of xy or yx, whatever order you want to put it in. And the last, I've got 3 times negative 1 for the coefficients, which is negative 3. Root of y times root of y is y. And again, if your brain went root of y squared, that's fine. Just finish it off then. The root of y squared is y. All I can simplify here is the middle terms. So just like when we FOILed in grade 9, we're going to put them together. If I have negative 2 root xy and then positive 3 root xy, how many root xy's do I have?
Root xy.
And then I'm just going to put the other terms. It doesn't really matter the order. So I'm going to put the 2x in the front and the negative 3y in the back. If you want to put all the terms that don't have a root together, that's fine as well. Order doesn't matter. That's as hard as the multiplication is going to get. How are we feeling?
Okay.
So we're going to go on to dividing, which really isn't dividing. And there are some things in math that are crazy. Just some. And there's some things in math that we do, but we don't know why we do. This is one of them. Mathematicians are typically left-brained, and left-brained people are really, really fussy people. When it comes to putting things in order, we have particular orders the way we like things. And left brains, you probably know what I'm talking about. When we put books, it either has to be by series or by author, or it has to be alphabetical, or sometimes, if you're like me, it has to go tallest to smallest, even if they're not in the same order. We all have a particular way we like to do things. Mathematicians are the same. There's some things we just don't like. So for example, we don't like when somebody writes the coefficient of 1. If somebody wrote 1x, it just irritates us, because we don't need it. We know it's there. If someone writes an exponent of 1, it irritates us. So if someone were to write this, it just drives mathematicians crazy. We don't know why. It just drives us crazy. We don't like it. We don't like with radicals when there's a radical on the bottom. Why? We don't know. It just drives us crazy. We think it's unfinished. Just like I would never leave 1x to the 1. What would I write that as? Just x. I would never leave a term with a radical in the bottom. So example number 1, I can't even look at because it drives me crazy right now. What irritates me about it? The fact there's a root 2 on the bottom. I don't know why. It's just the way mathematicians are. Is it root 3? Can't see that far. The root 3 on the bottom. It just drives me crazy. I can't even look at it. We just don't like it. So this is called rationalizing. It's not really dividing, but it's in dividing because they're fractions. So mathematicians are fussy people. And the first time I typed the notes, I put fuzzy people. We may be fuzzy, but that's not what I meant. I meant fussy people. And we don't like the look of a radical expression when the radical is on the bottom. We don't know why. So to get rid of the root on the bottom, we do something called rationalizing. And so what I'm really going to teach you in this next section is how to rationalize. I need to get that root off the bottom. Again, we don't know why, it just irritates me, and I need to get rid of it. So because this is an expression and not an equation, I'm really limited to what we can do mathematically. It's not like I can move it to the other side because it's not equal to anything. The only thing I can do when I have a fraction is I can multiply it by 1, because anything times 1 is itself. So when you have an expression, the only thing you can do is multiply it by 1, because it's the only thing that's not changing it. Well, this is where mathematicians get a little bit creative. Instead of multiplying by 1, I'm going to multiply this by root 3 over root 3. Let's talk about what I just did there. How is that 1? There's root 3s all over the place. Okay, you're a step ahead of me. I want you to just pause on that. I'm going to come back to that. How is this multiplying by 1? Ethan? Why is it 1? Yeah, because if you have the same numerator and denominator, we can cancel it to be 1. So I really haven't changed this expression. All I have done mathematically is times it by 1. I just got creative on what the 1 looks like. Why did I choose root 3 over root 3? Abby? Because on the bottom, a root 3 times a root 3 is a 3. So what's going to happen when I multiply top times top and bottom times bottom? 6 root 3 is going to be 6 root 3. The bottom is going to become, and then I can cancel the 6 divided by 3 is going to give me 2 root 3. To a mathematician, this is just prettier. This seriously makes me gag. The question, the answer makes me happy. Why? We don't know. It's just a left brain thing. This is called rationalizing. Rationalizing is when you're getting rid of the root on the bottom. Grab your calculator. I want you to calculate me the decimal value of 6 divided by root 3. So the actual question. Tell me what the decimal is approximately equal to. 6 divided by root 3. Approximately, can we confirm? Okay. I want you to calculate what 2 times root 3 is approximately equal to. Same thing. Well, that's why mathematically I haven't changed anything. I haven't changed the value of this expression. All I've changed is what it looks like. It's like repurposing. It's like taking something and making it into something else. I haven't changed the value. That's called rationalizing. It's one of the things I can't explain to you why. We don't know. We just don't like it. It's just called rationalizing. So to rationalize a numerical expression, you're going to multiply the top and bottom by the radical in the bottom. Or the radical in the numerator, if you like the math word, denominator, I should say, in the math word better. Radical in the bottom, radical in the denominator. Okay, so let's go to example 2 for division. Again, it's not really division, it's really just simplifying. Correct?
multiplying root 3 by itself?
Correct.
Okay.
And why? Just to get rid of it on the bottom, because it just annoys us.
All right.
So when I look at this in the mathematician, the top I could care less. It doesn't offend me. The 3 on the bottom doesn't offend me. What's the only part that offends me? The root 5. So the only way to get rid of it, because this is an expression, is to multiply by 1. What I'm just going to do is get creative what the 1 looks like. I'm going to take the top and bottom and multiply by root 5 over root 5. Okay? I don't care about the coefficient of 3. Numbers on the bottom don't bother me. It's just the roots on the bottom that bother me. So you might want to make a note to ignore coefficients. Don't include coefficient. Don't multiply by coefficient. Don't take the number, whatever makes sense in your brain. Numbers don't bother us. It's just roots that bother us on the bottom. Now we're just multiplying two fractions, so that's just top times top and bottom times bottom. For some non-visual people, I'm just going to give you a little hint here if you're auditory or tactile, sometimes if you cover the bottom, it makes the multiplication less confusing to your brain, because your brain only then sees the top part. So for some non-visual people, this is helpful. So coefficient times coefficient, 2 times 1 is 2. Radical times radical, so a radical 3 times a radical 5 is radical 15. Then what I'm going to do is just cover the top and just look at the bottom. Again, it's just fooling your brain into thinking there's not as much stuff.
Oh, yeah, that is better.
3 times imaginary coefficient of 1, 3. Root 5 times root 5, 5. And I'm just going to put that multiplication sign. Again, if your brain went to root 25, that's okay. Follow it through. Root of 25 is 5. Now I just need to simplify. Can I simplify a root 15? So is there a perfect square hiding within 15? So I just keep it to root 15. I'm happy with that. On the bottom, I would never just have a 3 and a 5 hanging around there. What would we do with them? Multiply, so 3 times 15. I told you the answer, 3 times 5. What your brain is going to want to do here is it's going to want to cancel those 15s. Because there's one on the top, there's one on the bottom. We've been nagging you for 3 years, cancel your fractions, cancel, cancel, cancel. Your brain is going to want to cancel those. But if you think mathematically, approximately what is the root of 15? 3.9. Has to be less than 4. So can I cancel approximately 4 with 15? No. So you cannot cancel a radical and a coefficient. I'm going to repeat that for the wordy people. You cannot cancel a radical with a coefficient. Again, your brain's going to want to do it because we've been nagging you to do it. What's the final answer? This is it. It's 2 root 15 over 15. Let's look at example number 3. Oh, this one offends me greatly. There's 2 roots down there. I can deal with it. It's okay. It's a little OCD, but I can deal. Now the problem here is, what do I multiply by? So if I pick root 5 over root 5, it's not going to get rid of the root 2. If I pick root 2 over root 2, it's not going to get rid of the root 5. What do I do when there's 2 different roots?
Do you subtract them?
Kind of. So we're going to use what's called the conjugate binomial. This word is going to come back to haunt you next year and the year after and in university. And you're going to be like, what's the conjugate binomial? And I'm going to be like, take out your notes from Unit 2 when we did grade 11 math. And you're going to be like, I don't have my notes. And I'm going to be like, yes, but you have your summary sheets. And this will be on your summary sheet when we're done the unit. The conjugate binomial is the exact same binomial, we just change the sign in the middle, and I'll tell you why in a second. We take whatever's on the bottom, we take the exact same numbers, we just change the sign in the middle. So for example, the conjugate of a plus b would be a minus b. We take the exact same terms, we change the sign in the middle. I'm going to repeat that in case you need that definition in words. Exact same terms, change the sign in the middle. And I'll show you in a second why we pick that. Change the sign in the middle. It's called the conjugate binomial. It'll come back over and over and haunt you in your dreams.
Oh my God.
So when do I just use the radical on the bottom, and when do I use this crazy thing called the conjugate binomial? When there's a binomial in the bottom. So if it's just one term, good to go. The problem is what do I multiply by when there's two? So I'm going to take the conjugate binomial of the bottom. I'm going to take the exact same terms, root 5 and root 2. But instead of putting a minus in the middle, I'm going to put a plus. That's the conjugate binomial. What do I multiply the top by? Well, this whole thing I multiply by still needs to be 1, because I can't multiply anything else without changing it. So if the bottom is root 5 plus root 2, what does the top have to be? Root 5 plus root 2. Okay. Exactly the same terms, opposite side. So sometimes brains can see better these are binomials when we bracket them. Sometimes it's a little bit easier to FOIL. If your brain needs brackets, then put brackets. Mm-hmm. I'm going to show you when we do the example. I'll tell you why. So top times top, bottom times bottom. Again, some brains it's helpful if you just cover the bottom and then you don't see too much and get overwhelmed. This is just a 2 times the bracket, so no big deal. 2 times root 5, 2 root 5. And a 2 times root 2, 2 root 2. And I don't care about those roots. I don't care. They don't offend me. It's just this one on the bottom that upsets me. Again, I'm going to cover the top, and we're just going to look at the bottom. How do we multiply binomial times binomial? FOIL or tic-tac-toe. Here's why we pick the conjugate. Watch what's going to happen. Root 5 times root 5. 5. The outside, root 5 times root 2. Root of 10. The inside term, negative root 2 times positive root 5. Negative root 10, and some people already see what's going to happen. And the last two terms, negative root 2 times itself, negative 2. And then I'm just going to put my division line back in. So right now you may be going, wait, but there's still roots. But what's going to happen?
They're going to be 0.
And that's what the conjugate does. It's the only thing that's going to cancel out the root. That's why we pick the opposite sign, is because we need one of those roots to be positive and one to be negative. It's the only way to cancel out that nasty root on the bottom. So to simplify it, top's not going to change because I can't simplify a root 5 and I can't simplify a root 2, so we just leave them as they is. Leave them as they is. On the bottom, those roots cancel, which is nice. I just need to put the two coefficients or constants together. So a 5 minus 2 is 3. This makes mathematicians happy. This does not make us go, ah. What's the only difference between the question and the answer? There's no root on the bottom. These mathematically are the exact same number. It just looks different. Why do we pick the conjugate binomial? It's the only thing that's going to cancel out those roots. Why do we need to change the sign? Because if I didn't, I would have had plus root 10 plus root 10. And when I simplified, I'd still have a root on the bottom. So the conjugate is the only way to get rid of those roots on the bottom.
Way to drive you being a mathematician and a lesson.
Actually, because I'm like a fake mathematician, because I just teach it, I don't do it. I really don't care about the roots, but I have to teach you. So.
Well, still, as a lesson, to drive you up the wall.
That's why I call myself a fake mathematician. I just show other people how to do it. I don't really do it all the time. I do. I enlighten the next generation. It's very powerful. The best part of my job, I tell my non-teacher friends, is I get to tell people if they can pee. It's the best part. Can I go to the bathroom? No, because I said so. Wow. Okay, you look at this, you're like, root on the bottom. Then you ask yourself, is there multiple stuff on the bottom, or is there just one single term? There's multiple stuff on the bottom. So that's a conjugate binomial question. Conjugate binomial is the exact same terms. So I'm keeping the root 2, I'm keeping the 1. All I'm going to do is change the sign. So the minus 1 is going to become plus 1. Again, it's called the conjugate binomial. It comes up in a whole bunch of other places in math. Well, if I multiply the bottom by this, I have to multiply the top by it. So root 2 plus 1. Going to highlight for the visual people. You'll notice the two signs here are always going to be the same. Some brains like the brackets to multiply. If you don't need the brackets, don't feel you have to put them. Just if some binomial times binomial, you need to see brackets. Again, some brains like to cover because it can be overwhelming if you're not visual that there's a lot of stuff going on. Okay, first times first, root of 2 times root of 2.
Or 4. Or 2, right.
Root of 2 times 1. One times root 2. 1 times 1. I'll simplify it up in the next step. Okay, now I'm going to cover the top. Look at the bottom. Root of 2 times root of 2. Root of 2 times 1. Negative 1 times root 2. And negative 1 times positive 1. Okay, so let's just look at the top first. Let's simplify. We can put the numbers together and we can put the roots together. So a 2 plus 1. And 1 root of 2 plus another root of 2 is 2 root 2. On the bottom, I can put the numbers together again. 2 minus 1. Root 2 minus root 2. If those don't cancel, you've done something wrong, because that's the whole reason why we're doing this process. So if you're a wordy person, you might want to make a note. If the roots on the bottom don't cancel, you've made a mistake. If the roots on the bottom don't cancel, you've made a mistake. Okay? Either you picked the wrong conjugate, you picked the wrong binomial, you multiplied wrong, but they have to cancel on the bottom. Well, take a look at what we have there. Would we ever write something like this? Oh, you're not a mathematician then. Drives me crazy. This does actually drive me crazy. What do we not need to have there? The one on the bottom. So what would my final answer look like? You got it. And again, take a look. This is what we started with. This is what it's equal to. To a mathematician, that's beautiful. How does all that turn into that? It's magic. Two skills you need to learn today are how to multiply